AP Chemistry, Hononegah High School. Today's notes will be finishing up section 13.5 and looking at section 13.6. Now, when we left off yesterday, we were talking about colligative properties, and we looked at vapor pressure lowering and Raoult's law. Today, we're going to look at boiling point and freezing point and osmotic pressure type situations. Now, non-volatile solute to solvent interactions also cause solutions to have a higher boiling point and a lower freezing point. So having a substance dissolved in water prevented the water molecules from evaporating as rapidly, and that would lower the vapor pressure of the water. That was vapor pressure lowering. Well, they can also affect boiling point and freezing point, in essence, for the same reason. Now, the change in boiling point is actually proportional to the molality of the solution. The equation we're going to use, or an equation we're going to fix in a second, would be the change in the temperature of boiling equals the K value times the molality, where Kb is the molal boiling point elevation. And that's actually a property of the solvent. So when you're doing this problem, you need to make sure you're looking up the K value of the solvent, and you also need to understand what you're actually calculating here is the change in the temperature of boiling. And since it's boiling point elevation, if you want to calculate the new boiling point, the calculated delta T sub B is added to the old boiling point of the pure solvent to calculate your new boiling point. Now, freezing point is freezing point depression, so now when you're calculating your delta T, you need to use the freezing point constant and still using molality, and you need to understand that this is depressing the old freezing point. So if you want to calculate the new freezing point, what you're going to be doing is subtracting the delta T that you calculate from the freezing point of the pure solvent. So with boiling, you'd add it to the old boiling point. With freezing, you would subtract it from the old freezing point. Note that in both cases, delta T does not depend upon what the solute is. It's only dependent upon how many of the particles are dissolved. Now, this type of calculation, as we see in these two situations, doesn't quite accurately predict what's actually happening when we dissolve different types of solids. Now, I'm not saying it's really about the identity, but ionic compounds, when they dissolve, give you a different number of dissolved particles than non-ionic substances like molecules. So we really need to incorporate another idea into these equations to make them accurate. So since these properties depend upon the number of dissolved particles, solutions of electrolytes, which dissociate in solution, ionic compounds, are actually going to show a greater change than non-electrolytes. So a molecular substance, which is a non-electrolyte, doesn't give you as many dissolved particles as an electrolyte would. And so in an ionic compound that breaks apart into ions. So to really more accurately look at boiling point and freezing, we need to take into account what we're actually dissolving in water in these two cases. Now, what we're going to use is what's known as the Van Hoff factor, and you should remember this from last year in AP Chemistry, and that's basically the I value that we're going to use to represent the number of particles that you get when a substance dissolves. Now, for non-electrolytes, molecular substance, the I value is just 1. But when you're dealing with an ionic compound, the I value is related to the number of ions that you get. So for something like sodium chloride, which has a cation and an anion, its I value is going to be 2. Whereas something like potassium sulfate dissolves into 2 K+ ions and 1 sulfate anion, so you get a total of 3 particles for something like potassium sulfate. Or something like magnesium sulfate, once again, it's like sodium chloride. 1 magnesium, 1 sulfate, you have an I value of 2. So to more accurately look at what's happening to boiling point and freezing point, we really need to take into account what type of solute we're dissolving in our solvent. So we're going to modify our two equations in this way to incorporate our I value. So a better way to do boiling point and freezing point would be to use this form of those two equations. So you'd look at the boiling or freezing point constant, the molality, and then you would fix the molality, in essence, for the number of dissolved particles you actually get by multiplying by your I value. Now, this is something we looked at last year, but in AP Chemistry, we're going to go a little bit deeper with this idea. What you need to understand is when you actually have a 1 molal solution of sodium chloride, that would dissolve to give you twice as many particles. So its molarity would be doubled, its molality would be doubled than compared to something like methanol. But the reality is you don't actually see NaCl giving quite a doubling of the freezing point change or the boiling point change. So it must be a little bit more complex. The I value of NaCl of 2 gives us a good estimation, but the reality is it doesn't quite double the boiling point or the freezing point as we would expect it to when compared to a non-volatile substance like methanol. So there must be something more at work here. Now what's really happening is 1 mole of NaCl dissolved in water doesn't really give you 2 moles of ions. Remember, sodium and chloride are oppositely charged particles, and when they encounter each other in the hydrated form and type of the solution, those particles can actually reassociate for a time. In other words, they can recrystallize and then later be redissolved. Well, what this effectively does is, instead of getting twice as many particles inside there at any given point of time, the reality is it's going to be slightly less than 2 times the concentration of the NaCl. So reassociations really are more likely to occur the more ions you have. So the higher your concentration is, the more your I value is going to change from the predicted value. So when you look at the substance like NaCl here, when the concentration is, we would predict its I value to be basically 2. That's known as the limiting value here. And at very low concentrations, it really does predict out to be very, very close than that. And how you actually get this is you compare your predicted value for the change in boiling or freezing with what you actually get. Remember, the difference between the two would be what the I value is. So that's where this comes in. Well, if it's actually only 1.97 times different, then it's not actually a full 2. And as you can see, as we increase the concentration, the I value differs even more than 2. So one thing that can affect our I value is really the concentration. I values are going to approach the limiting value, what we think they should be, the lower the concentration is. In addition, higher charge values have stronger attractive forces. Remember Coulomb's law. We're talking about ion electrostatic positive to negative ion attraction. So what we're really looking here at is a Coulomb's law type situation. So the greater the charge values, the stronger the attractive forces would be, the greater the reassociation is going to be. So when you look at these situations, sodium is a +1, -1. Potassium sulfate here is a +1, -2 situation, and magnesium sulfate is a +2, -2 situation. We'll take a look at what's happening as at any given concentration, we compare the numbers to the limiting value. So in something like NaCl, notice it comes very close to the limiting value of 2 at a low concentration. Something like K2SO4 should be about 3. Well, it's going to differ a little bit more from what we think. So therefore, we must be having more reassociation. And then when you get something like MgSO4, that's going to drop an even greater amount. So two things are really going to affect our value of I that you should understand. The greater the concentration, the worse our prediction is going to be for I value. And in addition, the greater the charges are of our ions from ionic solvent that we have, the more it's going to differ from the predicted I value. Now, the very last part of colligative properties is the concept of osmosis and osmotic pressure. Now, some substances form semi-permeable membranes. This is an idea from biology, so some of this discussion may remind you of something from honors biology a couple years ago or regular biology. So they form a semi-permeable membrane, allowing smaller particles to pass through, but blocking larger particles from entering. And that's why it's a semi-permeable membrane. Small particles will permeate the membrane or move across the membrane, but large particles won't. Now, in biological systems, most semi-permeable membranes allow water to pass through, but solutes are not free to do so. So in osmosis, there's really a net movement of solvent from an area of high concentration to an area of low concentration. So fundamentally, there's going to be a movement of particles. If we have this situation set up here in this U-tube, at the beginning here we have concentrated solution on this side, and we have a dilute solution on this side. Well, remember, Osmosis is going to involve the movement of solvent particles from an area of high concentration to an area of low concentration. So in this particular case, what's going to happen is we're going to get a movement of these particles overall in that direction. If we had a solution on the left side and a pure solvent on the right side, remember, we're going to get a movement of particles from an area of high concentration of solvent to a lower concentration of solvent. So we're going to end up getting a movement here. Now, osmotic pressure would literally be the pressure we have to apply to stop the movement of the particles. And in this particular situation, actually, I think I drew this one wrong. Let's back up a second here. If you take a look at it, it's area of higher solvent concentration to lower solvent concentration. If this is a dilute solution here, we're going to have a greater movement of our solvent in that direction. Osmotic pressure is what pressure we would have to apply here to basically stop that movement occurring. And that's why it's called osmotic pressure. It's a pressure we would apply to basically stop the movement across a semi-permeable membrane of our solvent. Now at this point, there is a video that I'm going to put on the school notes page as well that deals with osmosis and osmotic pressure that may make that concept make a little bit more sense, because if I just play the movie here, you're not going to actually be able to see it very well, because it really degrades the quality. Now the equation for osmotic pressure, how much pressure do we actually have to apply to prevent osmosis from occurring, is known by this equation. Now osmotic pressure, which is the symbol pi here, equals N over V times RT. Well, N over V would be molality. So osmotic pressure really equals MRT, where M is the molarity of the solution. Now, if osmotic pressure is the same on both sides, that basically means that the concentrations are going to be the same, and there isn't going to be any movement across the membrane, and that's known as an isotonic solution. So your book gets into different types of osmosis type situations here that you may remember from biology. So an example, osmosis in a blood cell. If the solute concentration outside the cell is greater than inside the cell, we call that hypertonic. And what's going to happen is water is going to flow out of the cell from an area of higher concentration to an area of lower concentration, and the cell loses its shape, and you end up getting what's called crenation. So basically the exterior becomes deformed as the cell contracts as the water leaves the cell. Now, if the solute concentration outside the cell is less than inside the cell, it's known as hypertonic, and what's going to happen here is water is going to flow into the cell, and you get a process known as hemolysis, and basically the cell is going to expand. If it's a great enough hypertonic situation, the cell can actually burst. And that gets us to the last section of the chapter, section 13.6, which gets into colloids and colloidal suspensions. Basically, a colloid, you need to understand that there's fundamentally three different levels when we make a mixture. You have suspensions, you have colloids, and at the smallest level we have solutions. We've spent most of the chapter looking at solutions. Well, a suspension is when you have a very large particle made up of individual ions or molecules, and those suspended particles that are inside the liquid aren't really so large that gravity is going to cause them to settle out. You get what's known as a colloidal suspension or a colloid. So a true suspension, you have very large aggregate particles, and those particles are so large that once you stop shaking or stirring the mixture, those large particles will settle out. If they're more dense, they'll sink to the bottom. If they're less dense, they'll rise to the surface. Well, if those particles are really not that large, the movements of the particles, basically the Brownian motion of the particles, which is what that's called, keeps those particles stirred up and dispersed even though they're not supposed to be. And you end up with what's known as a colloidal suspension. It should be a suspension that separates out, but it doesn't, and that's our colloid. There's lots of different types of colloidal suspensions that exist in everyday life. You can see over here, these are all different common products, and there are different types of colloids. Now, you don't really need to know the difference between an aerosol and a foam and an emulsion, but fundamentally there's lots of products in everyday life that we would like to stay mixed up, but yet they really aren't solutions. And if we can create a colloidal situation, then the solute-like particle that's inside there can say dispersed in the solvent-like medium, and we end up with a colloidal suspension. And in what type of colloid you have really depends upon the states of the different substances involved. So in common everyday products, there's actually a lot of different types of colloidal substances. Mayonnaise would be an example of a colloidal substance as well. Now, how can you tell apart solution suspensions and colloids? Well, one of the ways is to look at how light moves through the material. Colloidal suspensions can actually scatter light. So when you pass a beam of light through a solution, you don't see the actual beam of light because it's not striking large enough particles to disperse the light and make the light beam visible. But when you pass it through a colloidal or a suspension, so either a colloidal suspension or a true suspension, the particles inside are large enough to actually scatter light, and you get what's known as a positive Tyndall effect. So down here you can see the light moving through these two liquids. Now you do get a little bit of reflection of the light here on the glass, so you can barely see, if you look closely, a little bit of light. But you can see over here in the colloidal situation, you get a definite beam of light moving through that substance. So this would be an example of a positive Tyndall. And if we had a better type of glass here, this would be an example of a negative Tyndall. You really don't see the light beam moving through. Now, if you're standing in the forest and you can actually see sunlight moving through the air in the surrounding forest, that's caused by all the little tiny suspended particles that are actually colloidally dispersed inside the air, and you can actually see the beam of light. So that's an example of a positive Tyndall effect. And you can also see that light beams when it moves through atmospheric conditions, so sunlight traveling through. Now, as a general review of solutions, suspensions, and colloids, you need to understand that suspended particles are so large they're going to settle out. So yes, they would settle out. Colloidal suspensions should settle out but don't because of the movements of the solvent-like particles inside. And solutions, they're so small, they're evenly distributed, they will not settle out no matter how long you let them sit. Fundamentally, one of the biggest differences between the three is the actual particle size. Suspended particles have large particles. Solutions have very small dissolved particles. Colloidal would be somewhere in between. They're large enough that by density they should settle out, but because of the random movements of the particles, they stay stirred up. And the easiest way to tell the difference between these is put together the concept of, do they settle with the Tyndall effect? Because suspensions and colloids are going to have a positive Tyndall, but solutions won't. So if you know whether it settles out, you can tell the difference between suspensions and colloids. And if it has a positive Tyndall effect, you can tell solutions from the other two. Now, fundamentally, what type of mixtures do these form? Well, remember, we have homogeneous and we have heterogeneous mixtures. Suspensions and colloids are both actually heterogeneous, although with the colloid it's hard to see. To the naked eye it looks homogeneous, but on the particle level it really is heterogeneous. The only one that is truly homogeneous would be our solutions. Now, the very last thing that your book gets into is colloids as it relates to biological systems. Now, some molecules have a polar part, which is called hydrophilic. That stands for water-loving end, and a nonpolar or hydrophobic, a water-hating end. Now, in this molecule that you see here, the hydrophilic parts, the things that are going to be attracted, the water-loving parts, tend to be on the surface. And if you look, they're all over the place. We have some hydrogen bonding here. We have some hydrogen bonding there. We have ion situations in each of these places. So we've got a number of different things, as well as right here, that are actually going to be attracted to water particles on some level. So in this particular case, the hydrophobic parts are folded in and the hydrophilic parts are on the outside. So you would expect this thing to be attracted to water molecules and basically partially hydrate. So it can make, even though it's a very large molecule, it can make a hydrophilic colloid. So if the nonpolar parts are folded in and the things that are interacting with water are on the outside, you would end up with a hydrophilic colloid. If this is rearranged and your nonpolar parts are folded out and the hydrophilic parts are folded in, you'd end up with something that would not dissolve in water and end up separating out. So it would not end up forming a colloidal dispersion. Now, how can hydrophilic colloids form? Well, one way in which you can end up with a large colloidal particle that ends up staying dispersed is if ions get adsorbed on the surface. Now, this is not absorption to get drawn within. This is sticking on the outside. So this is adsorption. If you end up with a substance that doesn't have, this should say hydrophobic up here. If you have a hydrophobic substance, it really shouldn't form a colloidal dispersion. But if charged particles get adsorbed on the outside, then those things can interact with water. And what happens, it's really two parts. Not only can this interact with water, but these two things repel each other. So rather than clumping together and making a very large suspended particle, when you get this adsorption occurring, you can end up with these two particles retaining their size, not becoming too large, and yet being attracted to water molecules at the spot where you have ions. So really what the ions do is they stabilize the colloid and allow limited hydration, which prevents it from the nonpolar molecules from clumping together. So you get some ion-ion repulsion that helps with that stabilization. Well, that's one way that a hydrophobic substance can form a colloid. Another way that a hydrophobic colloid can form is if you have an agent that basically forms a bridge between the two. In this case, what we have is an emulsifying agent. So what really happens here is an emulsifying agent is a molecule with a polar and a nonpolar end, like soap. The nonpolar part would be attracted to the nonpolar substance we have here, like an oil droplet. And what it does is exposes then a polar portion to the outside. And this also ends up stabilizing an oil drop. This allows this to be attracted to water molecules at these positions. And also when these two drops get close together, they're going to repel each other. So once again, our emulsifying agent, like soap in this case, is going to stabilize the colloid and allow it to stay in a small enough form to form a colloidal suspension and not become a complete suspension as the particles start to recombine and you end up with too large of a particle. And that officially finishes Chapter 13.